Yes. So this is a COM drive. Then the resonance frequency can be calculated by this equation. Remember, it should be K over M square root. But the M here, MP, is this one, the shuttle mass. But we have 1 over 4 MT plus 12 over 35 MB. So MB is the beam mass. We have the beam here. We have the beam 1, 2, 3, 4. So MB is the beam mass. Then MT is the folded beams. I don't quite, but we can look into the original paper to find out the exact definition of MT and MB. Basically, they are the mass from the beams, because they will contribute to the total mass. Okay, so why do we have this 2 pi parameter? Kumel, why do we have this 2 pi parameter here?
This is the frequency value. Yeah, resonance.
So without 2 pi, what's the unit of frequency?
It's hertz frequency.
Huh? The unit for this F0 without 2 pi? Ahwan. Hugh, what's the unit for F0 without 2 pi?
R80 radian.
And
Omega, the unit omega.
over what?
Radian per second.
Okay, radian per second. With 2 pi, the unit becomes what? Kumel.
Radian plus.
With 2 pi, what's the unit?
Hertz.
With 2 pi, what's the unit of F0?
The unit will be the hertz.
Okay, hertz. Next page. Capacitive inertial sensor. And this one is a gyroscope. We need to apply this principle. The Coriolis force. Where's the word for? Anyway, we have an acceleration. This one is important. If we have two-dimensional vibration, what happened to another TA? If we have a mass vibration in two-dimensional, like vibration 1D and 2D. So now if we have a velocity in this direction, but also we apply a rotational acceleration. So we apply, while this one is moving straight, we apply rotational acceleration or rotational speed. While this one moving this way, we apply rotational speed to this object. So this is my thumb direction is the direction of this angular velocity. Then angular velocity cross to the v direction. We create an acceleration in angular velocity cross velocity. We get this acceleration. There's a force applied to this object. So this is Coriolis force. C-O-L-I-O-R-S Coriolis force, 科氏力. Have you ever heard the Coriolis force? Have you ever heard? You never heard Coriolis force. So I got, what is Coriolis force? What is Coriolis force? Can you repeat my explanation? Could you repeat my explanation?
The force which is applied on the velocity.
Tia, could you repeat my explanation? The Coriolis force. Repeat what I said.
Apply it and it will whatever it will play on something it will play currents.
Can you repeat what I said? No, you cannot. I mean,
Angular velocity cross velocity.
okay, then. Okay, you have velocity. What? Okay. I used several sentences to explain Coriolis force.
Have that and have force is this direction.
So can you repeat my words?
I didn't really understand.
One more time. If this car moving in this direction, if there's a rotational speed, we apply to this car in this way. So the angular velocity is in this direction. So this car will experience a force. The direction is direction of angular speed cross to the direction of velocity. So the sum direction is the force experienced by this car. So this force, omega cross V, we get a force. This force is Coriolis force. Repeat.
If the car moves this way, and we have the rotational velocity, the angular force will go this way, and the sum of two vectors this way and this way, angular force will be this way. This is the Coriolis force.
Outer product, vector A, outer product, vector B, we get new vector C. The new vector C, the direction is normal to A vector and B vector. And the magnitude of this outer product is magnitude of A multiplied by magnitude of B multiplied by the sine theta. Theta is the angle between vector A and vector B. So vector A outer cross vector B. The direction is the normal direction, normal to the vector A and vector B. The magnitude of this outer product is size magnitude of A, size of B times the sine theta. Theta is the angle between vector A and vector B. Kumil.
The force which we are talking, who is this?
Outer product. Now focus on outer product. Can you repeat my definition of A cross B?
Yeah. If we have a moving object,
No, no. Outer product. A cross B. Repeat what I explained about the outer product. Can you repeat?
If we have vector in this way and one vector in this way, the outer product vector will be this vector multiply this vector and side vector to
Can you repeat outer product?
Have two vector and have theta. So the total, the multiplied vector is like this, and so have the summarized force is this way.
Outer product. A vector A cross vector B is defined by magnitude of A times magnitude of B times sine theta. Theta is the angle between vector A and vector B. Alright, repeat.
We have two vector and we have the theta in the cross, and we all cross these two vector. We have the odd one vector.
Aga, can you repeat?
Between M and B have a theta, and M times theta and B is the
Outer product YT, inner product net T. Inner product equal to A dot B. Inner product is A magnitude times B magnitude times cosine theta. Theta is the angle between vector A and vector B. That is inner product. Outer product, vector A, vector B. A cross B equal to A magnitude times B magnitude times sine theta. Theta is the angle between vector A and vector B. Here, repeat. Definition of outer product of two vectors.
the outer product of two vectors is the magnitude of the vector A multiply magnitude of vector B and multiply the sine theta. Theta is the angle between two vectors.
Okay. So outer product, we had sine, we had the magnitude, and we had the direction of outer product. The direction is defined by the normal. So A, use right hand, four sums, A cross B. Then the direction of the sum is the direction of the outer product. Okay, R1, repeat.
Two vector and they outer product have the down way is the outer product, and between the two vector is theta.
Outer product is a vector, and the direction of the outer product vector is, we can use right hand rule. Direction of vector A cross direction of vector B, then the sum is the direction of the outer product. Hami, repeat.
outer product 改这个方向是 A vector A cross vector B，然后
Okay, so A vector A cross vector B equal vector C. So two vector outer product, we still have a new vector. But inner product, A inner A dot B, inner product is not a vector. It's just a scatter. Is the result is magnitude A times magnitude B times cosine theta. So let me repeat, listen carefully. Curvature force. We have a velocity of a body. In this body, we apply a rotational speed, omega, to this body. This body moving direction V, velocity V. So the direction of velocity is in this way. We apply rotational angular velocity. And angular velocity, if the four fingers is the direction of rotation, the sum is the direction of this rotational velocity. So the curvature force equal to omega cross V times 2. So now omega direction is here. Omega cross V. The sum direction is the direction of the curvature force. So curvature force is defined by 2 omega cross V. V is the linear velocity of the body. Omega is the angular velocity we applied to this body. So 2 omega cross V is the curvature force. Force is a vector. A vector means it has a direction and a magnitude. Kumia, repeat.
If we have a velocity of a moving object, if we will apply a directional angular velocity, the sum of the angular velocity will be the 2 omega and the angular velocity.
Outer product is not a sum. SUM is A plus B. That is sum. Outer product is cross, not a sum. Again, repeat. Repeat again.
If we have only velocity of an object, if we will apply an angular force to that object, so this outer product will be the 2 omega cross V velocity, angular velocity. The cumulative force will be.
So this is curvature force. Then, if we have this one, so you look at this object moving, we apply velocity. So this object, so inside this object, we have another object. We have spring, connect this one and this one. So if we move this one this way, this is the direction of velocity. Imagine this is the car, and in the car you use a ball. This ball is connected to the car. We use spring to connect the ball to the car. Now you're sitting in the car. The ball is connected to the roof of the car. So I drive the car. I move forward. I just keep driving. So now the ball and myself and the car has the velocity v. Now if I rotate. I rotate. So there's a rotational velocity. See? Rotational velocity this way. So now the four fingers is the direction of this angular velocity, rotational direction. So the direction of the thumb is the direction of this omega. So omega goes in, velocity goes this way. So the four fingers is direction of omega, cross V. So I get a curvature force downward. So this one is the curvature force applied to the ball. I can repeat.
So, if this is a pulse and inside ball, we have another tiny pulse, and this ball move this way. It has the velocity this way, and also we get the bus rotate around this axis, and this one will be this one is the angular velocity, and the omega based on the right hand rule. This one will follow the velocity of this direction, and the thumb will show the omega. This is the omega, and in order to define the driving force, curvature force, we use also the right hand rule, but the finger will follow this direction, and the thumb will show the driving force, curvature force.
The four fingers is the direction of vector A. Vector A cross vector B. We just from direction A rotate to direction B. Then the thumb direction is the direction of A cross B. Vector omega cross vector V. Omega direction is get is that way. V direction is here, so omega cross V, then we get the direction of omega cross V is downward. Repeat.
Okay. So we define the omega direction is in this direction, and if we have the omega direction and V direction, V in this direction, so this one will first it will follow the direction of the omega, and then it rotate follow the direction of the velocity. So this will be like this direction, and rotate to this direction. So the thumb will show the direction of driving force.
Okay. Suppose this one is in vibration. Vibration means vibrate. back and forth, back and forth, back and forth. Okay, vibration. Now the vibration direction this way, velocity this way, we can get a force applied to this one downwards. Now the vibration V direction goes this way, but the same direction of rotation. So now the angular velocity omega has a direction the same. 4 fingers is the rotation direction, and the finger is the direction of omega. Now omega goes in, and omega cross V, we rotate the 4 fingers from direction omega towards to direction of V. So now the sum direction is the force omega cross V direction. So but omega cross V is the force. Then now the force going this way. Come in. Repeat.
If this is a car object, suppose that the velocity which we are applying right now is this side. Okay, once we are applying the this direction of rotation of angular velocity in this way, the omega which is in the which crosses this object. Okay, once this is crossing the object, after that the force the force in between the omega sum of force omega and the velocity, so that the force which is on the outwards.
Okay, thank you. Now, listen carefully.
First, this one will go this way, so we have the velocity in this way. Okay, now we forget it. We have also another type of motion. This is the rotation. So in the rotation will create the angular velocity. So this kind of angular velocity, this direction will follow the right hand rule. So this object rotate this way, right hand rule, and the 4 finger will follow the arrow, and the thumb will show the direction of omega angular velocity, and it go inside the world. Okay, so we have the omega go this way, it's here, and the velocity vector is go this way at the beginning, I told you. So also based on the right hand rule, we the driving force will follow the, first we use the 4 finger to follow the omega direction. This omega direction is go inside the world, and from here it may be go this way or this way, but the first velocity will go this way, so it should go this way, and the thumb now go up, and this is the direction of the driving.
Okay, thank you. Okay, so now, so this one, vibration, and this one, because the curvature force, it will go down, up, down, up, down, up, down, up, down, up. So this is the principle we used for gyroscope totally. Okay, so velocity, we need to use, say, comb drive to drive this frame right, back, right, left, right, left. We use the comb drive. So this is the velocity created by comb drive. So we have sine omega t. So this is the driving frequency. And the velocity v. So we can use, this is omega, this is k, this is q. So imagine the vibration amplitude equal to f divided by k is the vibration amplitude, but this is speed. So f divided by k is the amplitude. The amplitude times omega is the velocity. We can show you some simple maths. You have a displacement x equal, say, x sine omega t. Then x dot dx dt equal to x omega cosine omega t. But x dot is the velocity. So velocity, the magnitude of the velocity is this one. The magnitude. Then see, x is the magnitude of x times omega. So that's why see velocity. So f divided by k, because f equal to ks. So x equal f divided by k. So f divided by k, f divided by k is the x. So x times omega is the magnitude of velocity. But now, for a transfer function, so this is the transfer function between, this is output, this is input. The transfer function. So at low frequency, so this is frequency. And output divided by input. This is transfer function t. So okay, so transfer function, output divided by input, this is transfer function. Y coordinate. X coordinate is the frequency omega. So at low frequency, this is 1. But at resonance frequency, the magnitude is quality factor Q times 1. So at low frequency, this is low frequency. We have x equal to this value. But at resonance frequency, the magnitude should be multiplied by Q. So that is why we have Q here. So F divided by K is the amplitude x, and x at resonant frequency, the X is amplified by Q. And the amplitude times omega r is the amplitude of velocity. So that's why we have this expression. But could you explain this? You cannot. Okay. Get a A4 paper, everyone, and write down your name and ID. And I will repeat one more time. And you listen carefully. After that, you can write down the process to write down this one. See, we have a spring. And we apply force F. So this is spring constant K. Force K. So K times elongation equal to the force. So X equal to F divided by K. So F divided by K is X. But remember, at low frequency, output divided by input, say, is 1. So input X, output X, the same. But at resonance frequency, omega r, input X, output is Q times X. So Q times X is the output at resonance frequency. And again, X is the displacement. This is the sine function. Then velocity is x dot ds dt. So ds dt equal to x omega cosine omega t. So the amplitude of velocity equal to amplitude of displacement times vibration frequency omega. So this is omega r. So that's why we use omega r times vibration amplitude equal to times this is x times q is displacement amplification. Displacement times omega is the velocity amplitude. Okay, try to write down what?
So this formula you sine omega t, and this formula cos omega t.
You can sine omega rt. So yeah, you can change this one to cosine and put a minus sign here. You just sine, cosine, they are just sinusoidal vibration. Okay, what can you, what time? (1:56). Okay, you write your answer and you can discuss with each other, and we will have 20 minutes break. Okay, I'll come back in 20 minutes. I'll turn this off. Now we are ready to start lecture 3, MEMS, accelerometer. Next page. So the purpose is to measure the acceleration of the device. So acceleration is velocity differentiation. Velocity is displacement differentiation. So acceleration is displacement differentiation twice with respect to time. Next. Usually, this is the spec for accelerometer. Dynamic range, say the acceleration, we have maximum value and minimum value. So this is the range, maximum amplitude of the accelerometer can measure. The unit is G. Usually we use G as the unit. So G equal to 9.8 meter per second square. So this is G value, 9.8 meter per square second. And the high frequency limit, usually it is the bandwidth of your device, high frequency limit. And the noise is it's not easy because we have electronic noise, we have thermal noise, we have vibration noise. In the circuit, we have flicker noise, we have Brownian noise, resistance noise. So we have a lot of noises. So it's we need to do it to measure it because we need to know SNR value. SNR, signal to noise ratio, is the basic parameter for any sensor. So you need to estimate the noise when you design an accelerometer. So noise, and we use spectral noise as because spectral distribution, y coordinate is the power of the magnitude, and x coordinate is the frequency. So noise is related to frequency. And nonlinearity, because for any sensor, for output and input, it's better to be linear, not non-linear. Because if you have a linear relation, if you get voltage, x coordinate is voltage, y coordinate is the acceleration. If it's a linear relation, if you know the voltage, you can use the slope to calculate the acceleration. So the relation between acceleration and voltage should be linear. But usually, the world is not perfect. Your device, if you do experiment, you will go up and down a little bit, like this. So your sensor, what? Again? Okay, you have voltage, x coordinate. You have acceleration, y coordinate. Usually, the perfect case is there's a linear relation. So we are happy. But in reality, if you do experiment for your accelerometer, you input acceleration, you get voltage output. Let's go another way. Acceleration, voltage output. You do experiment. It looks like it's not perfect linear. But if your result is this, you should be happy because we can use a linear curve to approximate the behavior of your sensor. But you need to tell your customer what is the nonlinearity of your device. So the nonlinearity is, say, this deviation divided by the measurement range. Then your customer will know, okay, when I buy this accelerometer, what's the nonlinearity? What's the error I would get from the measurement? Ahwan, what is nonlinearity?
Like the picture down that picture. non-negative and this linear.
Okay. Hugh, can you repeat my explanation? Nonlinearity.
Normally, if we in the perfect world, if we do the experiment, this is the y coordinate, this the x coordinate, this is y coordinate. The value of x and y is perfect in this way. But when we do the real experiment, it will have many unexpected results, like this point, and we will a curve like this. Compare the real curve like this one and the perfect one, the linear one. We have the error between the real curve after we do the experiment and the perfect. The difference between here is the non-linearity.
Okay, thank you. So the maximum deviation divided by the full scale. So this maximum deviation deviate from this straight line. The maximum deviation divided by the full scale is the way you calculate nonlinearity. Full scale. You tell your customer you can measure acceleration in this range. This is full scale, and this is, say, and this is maximum deviation. Maximum deviation divided by the full scale is the nonlinearity. Next one, cross-axis sensitivity. We have an accelerometer. We want to measure the acceleration in this direction. Okay, but now, suppose your sensor is X sensor, but now if there's a Y in our room, there's Y direction, vibration, Y input. In the beautiful world, your design, because your design is to measure AX. So if there's AY input to your sensor, your AX output should be 0 because you want to get the AX value. But this is not going to happen. For any sensor, if you have AY, it will create some AX output. So the cross-axis sensitivity means AX divided by AY. If you have AY input, but in the perfect world, AX should be 0. But if AX is not 0, your AX value divided by AY is cross-axis sensitivity. Next. The cross-axis sensitivity less than 1 to 3%, your spec. Nonlinearity, this one is nonlinearity, less than 1%. And frequency response, 1 to 5 kHz. So this is the bandwidth of your device. And shock resistance, if you drop your sensor to the ground. So if the impact acceleration is lower than 1,500 G, your device will be fine. Like your cell phone. Your cell phone shock resistance, if you drop it to the ground, if the impact acceleration is less than this value, probably your cell phone can survive. But if the acceleration is larger than this value, your cell phone may fail. So this is shock resistance. And this is dynamic range. for different sensors, we have different dynamic range you can measure. So if the range is small, maybe you have high resolution. But if the range is large, you have low resolution. I mean, what is resolution? Resolution. Kumil, what is resolution? Any idea?
Clearance.
The resolution say the minimum value increment. Say for this sensor, maybe your minimum increment of the output is 0.01 G. But for this device, the minimum increment you can read from your sensor output 0.001 G. So this one, so you can measure 0.901. You can read till the third digit after this point. But for this device, you can only read to the second digit. So you can only measure 48.04 G. But for this device, you can get 0.982 G. So this is resolution. Okay. Do you understand?
Yes.
Next page. Okay, we have different commercial products. Next. Now is the concept, the model of the accelerometer. So this is your accelerometer. You have a MEMS inside a box. The box is your accelerometer. You use spring to connect this MEMS to the box. Another spring here. And we have an electrode from the MEMS. We have two electrodes fixed to the box. We have modulation voltage Vm plus, modulation voltage Vm minus, AC. Then we have a capacitor S1, capacitor S2. So, okay, now you hold this box, your sensor. You sit in a car. If the car starts to speed up, then this one will move. And you can change the value of CS1 and CS2. By using this circuit, you can get voltage output. If you ask your driver, speed up quickly, you can measure V1. Speed up quickly, you can get voltage 2. So you can get a relation between acceleration and voltage output. So you do experiment, you can measure the performance of your device. Okay, so Agan, do you want to know how this works? Okay, good. Someone wants to know. Okay, in mechanical system, we have air inside the box. So we should have damping between this mass to the box, damper. Air resistance, the heat between air and your small mass, the energy dissipation. We use damper to model the energy loss. So this one is a resistor. You can think we have a resistor here. We have a inductor here. And this one is capacitor. In mechanical system, capacitor, inductor, resistor. So this is mechanical capacitor, mechanical resistor, mechanical inductor. Okay. And we use lumped parameter. Lump means this is lump. Like my hand, I have MEMS all over my hand. So I have many small MEMS. But it's too complicated to model each MEMS along this hand. So I would put the total MEMS of my hand into one point and say the point has a distance to my shoulder. So I put everything into a MEMS, not distributed MEMS. So put everything into one small tiny point is a lumped parameter model. I mean, what is lumped parameter model? All right, what is lumped parameter model?
Like the continuous model. They connect together. Like the parameter itself.
And here, what's your answer? Lumped.
I don't really understand about the mesh and put on the mesh inside the code.
消防广播设施，本栋大楼稍后将设置消防设备，如有听到警报声响，请勿惊慌。稍后设置
We have a bit.
设备，听到声响，请勿惊慌。
Look carefully. We have a bit. We create. We apply a force F. Then the beam has a displacement X. So the beam has you can so each beam element has a mesh. Okay, you can use software to create a mesh and apply force and get the displacement. A software element, not other elements. But also you can model this beam as only one mesh. And so here is a spring. So you apply force F. You can get the same displacement, X. So we create this model only one point to represent this beam. So this is lumped model. This is distributed model. Means you distribute everything in the body. Distributed model. This is lumped model. But to have a lumped model, you need to know the K value. But how to get the K value? You can use theory, mechanics theory. You can apply F, then calculate moment and reaction force, then cut here. Then this is mx. mx divided by EI equal curvature. Then this is y second differentiation. So you can solve this differential equation, PDE, and get y as a function of f. So if you do f divided by y, you can get k value. Then you can use this k value to use it in the lumped parameter model. So what is lumped parameter model?
Lumped parameter model is we use only one element to represent for all of the elements of the field. So, and to build another model and put that point into that model.
So for a sensor, it's not, it has inside the box, sensor box, the accelerometer, usually, next page, next, 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 next. Okay. Next, 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 next. Okay. So this is an accelerometer. We have a package. Package is the box. And inside the package, you have the chip. You have shuttle mass, you have cone, you have spring. So it's distributed element model. Okay, then go back to our page. Then we can use this simple model to represent that distributed element model. We just use one mass, use spring constant K, use damper. So this is lumped model.
The lumped model is for calculation, and the distributed model is the real model.
Yeah, and lumped model is easier for you to get you can understand the behavior of your system. Because for small system, it's simple. But you have a big system, like you have space shuttle. You want to model the space shuttle. It's almost impossible to model all the components in a space shuttle. So you better to simplify your complicated model into several small systems, small model. Okay, next page. Then, okay, previous. For this model, we can you clean this? I'll do it here. No? Okay, fine.
那个因为已经储存的，所以要跳出去外面，然后把它删掉。
Oh, don't worry, I'll just do again. Okay, if we have this simple model, we apply force F, then this one will become, so, okay, next page. So for a system, we apply a force, then the spring becomes longer. So this is original position. So we use x coordinate to represent the position of the mass M. Now we take this mass out. So we have external force F, but the spring has a recovering force. Spring force recover. So the spring force equal to spring constant K times displacement X. But if you move the mass to the right, you have resistance force from the air to stop you more. So you have the friction force from air. So we can use B times velocity. This is the model we used to model the resistance force from air. Then we apply, so this is Fext. So we apply Newton's second law. Total F equal to mass times acceleration. This is Newton's second law. So this is x coordinate. So to the right is positive, to the left is negative. So Fext to the right, Fext, Ks to the left, minus Kx. Bx dot to the left, minus Bx dot, equal M times x double dot. So M x double dot, we move this one and this one to this, the right hand side, Bx dot Ks, Fext. But if Fext is a sinusoidal signal, this is amplitude, this is frequency, time. Okay, everyone, draw this figure and derive the equation like what I did, everyone. Camera off.